Hello, my name is Tilman Milzo, or just Till, and welcome to the talk on training neural networks as ERcomplete. This is joined with Mikkel Abrahamsen and Linda Kleist, and let me mention that authors are ordered alphabetically. This is Linda, this is Mikkel, and let me start with this short recap on what neural networks are on a high level and what it means to train them. So a neural network is yes, somewhat a directed graph, and it usually is organized in layers classically, and we have these input layers, we put in the data, and then we do some processing where this data goes through the graph, and then the neural network gives us some output, which we could usually think of an output label. And usually what we do in training neural networks is we compare it to a label that we already know from the data, and we want those two to be the same. And in that way, we manipulate these weights and biases inside the neural network. So that's a very rough summary of what neural networks are. So the way that we train them is that we usually change a little bit each of these weights and hope that we get better. And then in that way we get better and better and better, and that's somewhat often successful, but the kind of best method we have at the moment. So this tuning all these parameters is called gradient descent, or sometimes stochastic gradient descent, or backpropagation, which is again just a different name for gradient descent, and it has a few downsides. The first downside is it can take and will take an infinite amount of time to reach the optimal settings of the weights. And that's also not just a theoretical problem, it's also a practical problem, because sometimes we do have a good network architecture, but it just doesn't happen to train, and sometimes we don't, or often as a user we don't know, is it because we set wrong the hyperparameters, didn't set up the stuff correctly, or maybe just the data is inconsistent and we can't actually get a better error. It's also unreliable. Like, even if we have the best solution, we do not know it's the best solution, right? Just like, well, that's the stuff we got after trying a long time and we don't see how to get better. That's not a reliable result. Specifically, if there's not a good solution, then we would like to know there is not a good solution. And at last, training neural networks is very resource intense. If you look at these results with AlphaGo, there was 9,000 TPUs trained for a day. It's gigantic, the amount of resources we need. So the network question is, could we do something better, or could we not do something better? Okay, we come back to that question. At last, so we cannot use other tools that we use for problems in P. Another notable remark is that for many classical tasks, neural networks perform best. So this includes language processing and image recognition. I think these are two of the main applications of neural networks, but for instance also deep reinforcement learning. Recently I saw there was a paper on the three-body problem in physics. That's like how the movement of three bodies will develop over time, which is difficult to compute. And so somehow the question that we want to partially answer, or at least give one perspective on those two questions, is why are neural networks so good, and why do we need to use backpropagation, i.e. gradient descent? Note that there are lots of different perspective angles on that question, but here we give one of them. Namely, what we do is we determine the worst case complexity of this training neural network problem, and we determine it as ERcomplete. And I will explain what ERcomplete means in a few slides. So let me note that here the activation function is just the identity. So already with very simple neural network, or very simple activation functions, we have hardness. The cost function can be anything reasonable, because we want somehow the cost to be zero in our hard instances, but you can also make it a larger threshold by just adding inconsistent data. Yes, and I think I should maybe mention that our neural network has 2 layers, but not 2 fully connected layers. So our networks are weird, but they are having only 2 layers, 2 hidden layers. So two sets of these edges. Okay. Okay, so let me now explain what does this mean, this existential theory of the reals. So let me start with the definition. So we have somehow this term existential theory of the reals stands for 2 things. First, it stands for an algorithmic problem, and it also stands for the complexity class of all problems that are equivalent to this algorithmic problem. And this algorithmic problem is like we have some weird formula, and we want to know whether there are real numbers that satisfy this formula. And this formula can consist of variables, constants, addition, multiplication, logical operators, and equations and inequalities. Okay, so this sounds a little bit abstract. So it's something just very general, and here's a good example. So we have this, we want to find if there are 3 numbers, 3 real numbers, such that some equation equates to 5 and some other inequality is not larger than 5, like this term is not larger than 5. And you can have all types of these combinations. And note, while I didn't formally allow 5, you can build 5 easily as 1 plus 1 plus 1 plus 1. And while x squared is also not allowed, you can just as a shorthand notation for x times x. Yeah, and in general, these problems are extremely hard to solve. I mean, people who work on these types of algorithms in real algebraic geometry, they will tell you, no, we're really great at it, we can solve it for up to 12 variables. And they're really excited. But if you want to use this to solve any practical problem, 12 variables are way too little, and I will come to this again. But that's now all problems that are equivalent to this form the complexity class of the existential theory of the reals. And so what makes it interesting, the existential theory of the reals, is because we already know about a broad set of problems that are complete for it. So 2 problems that I personally worked on is this geometric packing. So we have given a container and we have given items, and we should move these items into the container without overlap and we are allowed to rotate. Then another problem I worked is the art gallery problem from computational geometry, where you think of you want to place guards such that everything is seen inside this so-called gallery or just simple polygon, but also problems related to graph drawing, Nash equilibria, and polytope theory. Just to give a few examples, are related to the or are ERcomplete, and there are many more. So by now we have kind of established this complexity class as being fundamental and touching on many different areas within mathematics and computer science. One common theme is that for all of those problems, they're very hard to tackle. So usually what we do in combinatorial optimization, we cannot really do for those problems, or only to a very limited extent. So this is more of an experience than something that is provable. But maybe what we can say is, for many of these methods, if they would be applicable directly, then that would mean that ER and NP are the same, which we do not believe. Another aspect that I want to highlight here is that how difficult it is to solve these problems. So here we have 11 unit squares, and we want to find the smallest container containing 11, smallest square container containing 11 unit squares. This is strange, but currently best known solution, but we do not know if it is the best solution. And if you have an instance of an NP complete problem of size 11, you just have a brute force algorithm and you just do it. And here, it's not just that we don't have a brute force algorithm. We do not know. People have written papers on this and they do not know the optimal solution. And maybe if a lot of researchers would put in a lot of energy, they may be able to prove that this is the optimal solution. But then, I go to something like 17 and boom, or 8, or I don't know, 18, 19, and boom, suddenly, you have another year of many PhD students to work on if you want to, and maybe they will never find the optimal solution. So it's really, these problems are worst case much harder to solve. That doesn't mean that we cannot do something about them, but just to put this into perspective with other complexity classes. So there's this very famous complexity class NP, and it's kind of trivial that it's contained. NP contains this existential theory of the reals. The existential theory of the reals are contained in P space, and the membership comes from using symbolic methods or using methods from algebraic geometry, where you basically use algebraic structures and don't. That's somehow what you do. I'm not very good at these methods either, and few people understand them in my area. So I guess you have to be an expert in algebraic geometry. And yeah, so somehow now we come back to what I told you in the beginning. So it is no surprise that once we can train neural networks, they can solve problems that other methods cannot solve, because they really solve a problem that is ER-complete instead of just NP-complete. So somehow neural networks turn out to be a tool which can tackle problems that are harder than NP. So that can explain the success. But also it explains why or it gives a perspective on maybe why this gradient descent method is possible, because if we could solve this using dynamic programming, even if this dynamic program would take an exponential amount of time, that probably would also prove that the problem is contained in NP. And so far we believe that these two complexity classes are different, but of course we don't know. Also, I should say some caveats. There are different ways of looking at neural networks. You can look at approximation. If you don't believe in worst case analysis, but somehow from a complexity theory point of view, we would like to have more than just worst case analysis. But unfortunately, that's the tool that we have, and it seems to be a very robust yardstick on how difficult a problem is. But of course, you should not take this as a whole picture. Okay, I want to end with some open question. So I told you that these networks for which we have hardness are two-layer networks, but what about fully connected ones? So then really the difficulty needs to come from the data. It's also kind of trivial that for fully connected two-layer networks, they can be solved with Gaussian, the Gauss algorithm, because it's just matrix factorization if the activation function is the identity. So here you need to have as an activation function a ReLU, which I don't think is a hard constraint because ReLUs are used ubiquitously in practice. So I think this would greatly strengthen our intuition and would show that this ER completeness comes up very quickly in practical examples. I think it would very nicely complement other work on theoretical work on both on ER completeness as well as on neural networks. Okay, thank you for your attention.